The future of additive manufacturing in industrial series production. The IDAM research project has shown the way forward. For the first time, a production line has been fully automated and digitalized. The transport of the build frame, the unpacking of the build job, and its depowdering, the separation of the finished components from the substrate plate, the preparation of the used metal powder, all these process steps take place fully automatically and without manual intervention. The aim of the IDAM project was to significantly reduce production costs through consistent automation and digitization of all process steps. 12 project partners from German industry and research institutes were involved in the project. At BMW and GKN Additive, the ideas were implemented in production systems.
During the IDAM project, we were able to demonstrate the future of additive manufacturing within a continuous flow production. Together with our partners, we have already established that this type of automation concept can already be used with the current generation of 3D printers. I'm sure that the solution, which was developed in the IDAM project, will soon be commonplace in an everyday production.
A demonstrator system is located at GKN Additive, a division of GKN Powder Metallurgy in Bonn. The system uses a 3D printer type EOS M300-4. The printer transfers the finished build job to the building frame transfer station. Here, the build frame is closed with a lid and prepared for transport in the production system. The GTAS transfer system is responsible for transporting the build frame and the build job between the stations. As an interface, it automatically adapts to the different transfer points of the machines.
The flexibility of the GTAS transfer system gives us a chance, depending on the operational model, to use either an automatic guided vehicle or a manual transport system. This is enabled by the complete modular approach taken within the IDAM production line.
The IDAM project has set new standards in unpacking and depowdering the build job. For the first time, this is done fully automatically without manual activities. Previously, the state-of-the-art was unpacking and depowdering in several steps, which also required manual work. The new depowdering station offers, in addition to the high level of automation, very good cleaning results, complete recovery of the metal powder, and at the same time, optimum protection of personnel from dust. For depowdering and cleaning, a depowdering hood docks onto the build frame. Together, both are rotated through 180 degrees. The majority of the powder empties under gravity alone. Therefore, special compressed air nozzles blow off the build job, cleaning powder from any small crevices. Finally, by the use of a material vibrator, any bridges or conglomerates of powder that remain are removed to maximize the cleaning efficiency. The quality of the cleaning of the components is normally so good that subsequent cleaning steps can be dispensed with. The metal powder is collected inside the station and buffered in a container. After cleaning, the build job and the build frame are separated from each other. The build frame is closed again with the lid and forwarded to the GTAS transfer system. It is then moved to the assembly station, equipped with a substrate plate and made ready for the next build job. Now it is the turn of the build job. From the swivel arm, it is brought to the sliding door, where it is transferred to the GTAS. The GTAS now takes the build job to an automatic sawing station. The components are cut off from the substrate plate. The substrate plate is then reprocessed and used again in a build job.
The depowdering results exceeded our expectations, including the removal of most of the dust from our build box surfaces. This simplified all of our subsequent work steps. However, the plus in occupational safety was also important for our employees. Thanks to the removal of the dust, our colleagues can now dispense with the cumbersome personal protective equipment.
The Depowdering from Volkmann is used for the reprocessing of the used powder. The used metal powder is extracted from the depowdering station and conveyed through a pipe by means of vacuum conveying into the Depowdering. In Depowdering, the powder is sieved, agglomerates of several powder particles, broken support structures, and other oversized particles are removed. The clean metal powder is then conveyed through a pipe to the supply container of the printer. Again, vacuum conveying is used for this purpose. A second demonstrator system is located at BMW's additive manufacturing campus near Munich. This system differs in some details from the GKN system. For example, a Trumpf TruePrint 5000 printer is used. A GTAS transfer system is also used in this arrangement. A driverless transporter moves it between the stations. Build cylinders from Trumpf are used as the build frame. The metal powder is handled and transported in supply cylinders. These supply and build cylinders can also be buffered in an intermediate storage facility. The depowdering station is also designed for Trumpf build cylinders. A powder preparation station developed by Volkmann is used for powder recovery. As with the Powtrex system, the agglomerates and foreign bodies are separated by a sieve. This station additionally handles the blending of recycled and virgin metal powder. A homogeneous mixture is produced in an adjustable blending ratio. This is filled into supply cylinders and forwarded to the GTAS transfer system. In the powder preparation station, the metal powder is also dried by means of a vacuum. The drying process verifiably improves the quality of the printed components. The difference in flowability is clearly shown by an examination in the laboratory. Two samples of a stainless steel powder are compared here. Both samples had previously absorbed moisture from the air. However, one sample was subsequently dried by means of vacuum. The humid powder is very lumpy, while the dry powder flows very smoothly. With a humid metal powder, imperfections occur when applying the powder layers in the 3D printer. With some metals, the bound water also creates pores in the component during printing. In summary, it can be stated, the IDAM research project has demonstrated that complete automation and digitization of additive manufacturing is already possible today. Established technologies and new concepts have been combined to form a holistic production system. Automation can significantly reduce production costs in series production, an important step ahead into the future of additive manufacturing.